Sir, good morning. Thanks for joining.
Thanks. Thank you very much. Thank you.
Let us wait for another 4 minutes, sir.
Yeah, no problem. Can I? Okay, let it. There is a slide, so okay, that's fine.
சாப்பிட்டீங்களா?
ஆச்சு.
Right.
ஆமா.
Sir, Ganapati sir.
சார் சொல்லுங்க சார்.
10 o'clock start பண்ணிக்கோங்க சார்.
ஆமா சார், ஆமா சார்.
Okay, fine, thank you sir.
Thank you.
Naveen, voice audible இருக்கா?
Yes sir.
Okay.
Sunbrasser, just for information, actually many professors are connected in the online.
Okay.
Our students are listening from LCD projector. Actually.
Okay, no problem. I hope my voice will be clear to all.
Yes.
Yeah, okay.
Yes, audible.
Thank you.
Yeah.
வந்து என் பாட்டுக்கு ஸ்கேன் எடுத்து வரீங்க ஆள் வந்து வரீங்க பாத்துடா யாரும் உள்ள வராம ஆமா அந்த பக்கம் உள்ள வந்து அவங்க
Naveen, voice audible இருக்கா? Naveen? கேக். Ganapati sir, shall I? Ganapati sir, shall I start?
Yes, you can start now. Yes.
Yeah, thank you so much. Simple life is the key factor for all kind of happiness. Simplicity makes us genuine. Simplicity makes us neat. Finally, simplicity makes us a manly man. So is Swami Vivekananda. And our college is very proud to bear his name on our crown. His Excellency, founder, the great Swami Siddhananda Maharaj, Secretary Swamiji, Gulapati Swamiji, the dynamic principal, head of the department, convener of this program, resource person, organizing secretary, treasurer, faculty members from our neighboring colleges, our own department, student participants, and ladies and gentlemen. With these words, I heartily welcome to the holy ambience weather. Today is a great day to our institution. Yes, VPG and Research Department of Chemistry is organizing an one-day online FE faculty enrichment program on needs and matrices of green chemistry under DPT Star College scheme through online mode. We people always hope a holy electromagnetic radiation that has been always received from our founder, and each single sand particle of our campus can be activated by our powerful enchants. So with this, let me click this online Feb meet with our usual college prayer, Om Shahana Bhavatu. Yes.
ॐ शगना ववतु शगनौ पुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः.
Yes, thank you so much. Yeah, a beautiful word in the dictionary. Even it doesn't know religion, doesn't know caste, and so many things. It's a single word, even connecting an unknown person, nothing but welcome. So, in this regard, I privilege to feel to welcome our most active and dynamic leader of our prestigious department, Mr. B. Servaramuthu sir, Head and Assistant Professor, Department of Chemistry, Vivekananda College, Thiruvedagam West, and also the Department Coordinator of this DPT Star College program to welcome the gathering. Sir, please.
Pleasant morning to one and all gathered here. I'm very happy to deliver welcome address. First of all, I submit my humble pronouns.
கேட்கல.
Okay, fine. Raja, am I audible?
Yeah, sir, you can proceed.
Sorry, little bit technical issues. Right. I'm very happy to deliver welcome address in this August meet. First of all, I submit my humble pronouns at the feet of our founder Swamiji, Swami Siddhananda Maharaj, Secretary of our college, Swami Vedananda, Kulabadi, Swami Adhyatmananda, the dynamic principal, and today resource persons, my dear colleagues and my dear students. Very warm welcome to one and all who are connected in this online. First of all, I submit my wholeheartedly welcome to our Secretary Swamiji, always blessing us, supporting us, motivating us, encourage us to do a lot of things like online FDP program under TBT scheme. Then I welcome for dynamic principal, Dr. T. Venkatesan, who is always part and parcel of our department. With his encouragement, supportment, we are able to conduct this type of activity. So I welcome you, sir, of the department. I'm very happy to welcome today resource person, Dr. Sanmuga Raju, Assistant Professor at Department of Chemistry, Indian Institute of Technology, Palakkad. So really we are honored to have such an eminent personality with us, who is going to talk about emergence of supramolecular chemistry from molecules to materials. So because of the college and the department, I submit a warm welcome to you, sir, for this meeting. Next, I welcome dynamic convener of this program, Dr. M. Kanambadi, sir. Whenever I give any work to him, he plan meticulously and he plan in a different manner. Like that, today also he has planned very well, excellently, and he is doing his job perfectly. So, on behalf of the organizing team, I submit my warm welcome to you also, sir. Then I welcome organizing secretary Dharmanandam, sir. Then I welcome all our faculties members. With their support, I'm running the department in excellent manner. Then I welcome the master of ceremony, Dr. L.A. Raja. Then I welcome all the participants from various institutions, various colleges who are connecting in this online. Finally, I welcome my students who are sitting in front of a smart board. They are watching the program. So I welcome you all, my dear students. Again, on behalf of the management, college, department, I welcome you all to this event. I pray to God to get success this program. Thank you so much.
Thank you, sir, for your extended welcome address. So with this, sir, whether principal is there, sir? HOD, sir?
Wait. No. Due to some busy schedule, he is unable to participate in this event. Just proceed to the next one.
Okay. Thanks for your information, sir. So as our principal is adjoined with an important meeting, he could not able to join in the same meet, but we believe he's a man who always been connected morally in all aspects. In absence here, we submit a hearty thanks for our kind acceptance. So we Vivekanandans are always under the holy umbrella, which always allow the transparent light as blessing mutually from our Secretary Swami Vedananda Swamiji and the Gulabadi Swamiji. In absence here, we bow our siram at their holy feet to believe and receive their blessings always to initiate this meet. So with this, now we move to the technical session. And today we have a very big shorts. Dr. S. Sanmuga Raju, Assistant Professor of Chemistry, IIT Palakkad, and Dr. Arindam Indra, Assistant Professor of Chemistry, IIT Varanasi. And for participant shake, we have more than 79 participants in online mode and more than 120 participants in offline mode at our college campus. With this, now I would like to invite my friend Dr. G. Rajkumar sir, Assistant Professor, Department of Chemistry, to chair this session. Sir, please.
Thank you, Eli. Am I audible?
Yeah, you can proceed.
So I'm very happy to introduce today's resource person and chair the session, the first technical session. So today's first technical session. So the resource person is Dr. Shanmuraju Sankarasegaran sir, Assistant Professor, IIT Palakkad. So the beautiful flower blossomed from the garden of one of the prestigious institution in Madurai, Tamil Nadu, the American College. So sir has got his BSc and MSc degree from the American College, Madurai, Tamil Nadu. So sir did his PhD under the in the Institute of Science, Bangalore. Sir was awarded Professor S. Soundarajan Gold Medal for the best thesis. Sir has also got postdoctoral research from abroad. So Sir was worked as research associate in the Department of Inorganic and Physical Chemistry, Indian Institute of Science during 2013, and Sir is a postdoctoral fellow of Irish Research Council, Trinity Biomedical Sciences Institute in Ireland during 2013 to 15. So during 15 to 2018, Sir was worked as a senior postdoctoral fellow in Ireland. So currently, Sir is working as assistant professor in chemistry, Indian Institute of Technology, Palakkad, Kerala. Regarding his research area, so the supramolecular structures and materials. So to his credit, Sir has published more than 50 research articles in well-reputed journals. So I can name the few research titles. It's a main group supramolecular chemistry and development of a new synthetic methodology for the design of luminescent organic materials and KH2 network approach, porous organic and hybrid polymers. So regarding his awards and fellowships, so Sir is a member of Royal Society of Chemistry, and also he is a reviewer for well-reputed journals, nearly 20 journals. Sir is serving as a reviewer. And regarding his membership, so he is the active member in various professional bodies. So his love and passion towards research has been reflected from the research projects. So Sir has got nearly 2.2 crores. No. So Sir has got research projects from Europe country, United Kingdom, and Ireland, and Switzerland. It goes on. So Sir profile is running about 16 pages. Okay. So due to time constraint, so I have limited. So I have shared only few informations about today's resource person. So with these kind words, so let me invite Dr. Shanmuraju Sankarasegaran sir to deliver an invited lecture on emergencies of supramolecular chemistry from molecules to materials. Over to you, sir.
Yeah.
Sandra, sorry for the interruption. Let me tell you something. You can have a presentation for 1 hour. Then maybe another 10 minutes the students or the faculty can interact with you, sir. Okay. Yeah, that's the way we can go. Thank you, sir.
Okay. I hope my screen is visible. Yeah.
Yes, sir, it is visible, sir.
Is it moving?
No, sir.
No, it's not moving. Yeah, I think this was one problem I had earlier. Okay.
Sir, make it slideshow.
Yeah, slideshow mode you can.
Yeah, in slideshow mode there was a problem and it's not changing. So, do you see it's changing my slides?
But it's not big as we have to see. It's very small.
Can you see the slide? Is it?
No, we can see the slide, but it looks very small. Maybe can you convert it into PDF file? Then it's easy, right?
Yeah, sir, that's good actually.
Okay. Yeah.
Just convert it into PDF, sir. Then.
Okay.
Prabhu, good morning.
Is that fine?
Yes,
Yes,
sir.
looks good. Looks
It is
good.
fine.
Okay. So I put it in a PDF mode. Okay.
But we can change it in the full screen mode here also, right?
Yeah. Is that fine now?
Looks perfect. Good, good, nice.
Okay, perfect. Thank you very much. So first of all, I welcome everyone to this presentation, and a special thanks to my senior, Dr. Kanapati, for his invitation to deliver this talk. Also, I thank the head of the department and organizing committee and Dr. Rajkumar for the kind introduction. And yeah, so let me go into the supramolecular world. So for another 1 hour, I am going to take you all to the supramolecular world, where I will be talking mainly about what is supramolecular chemistry, where from the field of supramolecular chemistry started, and then I will introduce the concept of host gas chemistry. And within host gas chemistry, how one can use the reversible supramolecular self-assembly as an alternative synthetic tool to design the targeted macrocyclic system. And among various non-covalent interaction, and we are particularly interested in using coordination bond as a driving force to design a large supramolecular complex. So I will be discussing in particular how we can use a coordination bond as a driving force to design a large metallocycle and metallocages. So beside their synthesis and characterization of coordination-driven self-assembly structure, I will try to highlight a few selected applications of self-assembly metallocycle and metallocages, focusing on environmental related application as well as the biomedical aspects. So at last, I will highlight some of our recent findings in the area of project-based containing supramolecular structure and their material, including their application. Okay. So as you all know, chemistry is all about making a new molecule or understanding the existing molecule or the molecule which we make, their reactivity and their function and their properties. Okay. So if you ask a supramolecular chemist, they will classify chemistry into two categories. One is a molecular chemistry, another one is a supramolecular chemistry. Okay. So chemistry is a very broad subject where you can find plenty of sub headings, start from inorganic, organic, physical, nano, and so on. But as an inorganic chemist or supramolecular chemist, I classify chemistry broadly into two categories. One is a molecular chemistry, another one is a supramolecular chemistry. Okay. So what is a molecular chemistry? Chemistry of covalent bond. Okay. So for example, if you take this two object as a molecular precursor, which means it may be atom or a cluster of atom. If this atom react or the cluster react covalently to form a molecule, something like this, and this we consider as a covalent chemistry. Understanding their properties, reactivity, and their function comes under molecular chemistry. Okay, so that's why the definition of molecular chemistry is nothing but the chemistry of the covalent bond. So if you look back the history of molecular chemistry, it goes back to 1828 when Uller synthesized the first artificial molecule urea from the inorganic precursor. Okay, so the history of molecular chemistry is almost more than 120 years old. On the other hand, if you ask me what is supramolecular chemistry, and the definition of supramolecular chemistry was given by one of the leading proponents, Professor James Learn, who is a Nobel laureate in chemistry, supramolecular chemistry, and he defined supramolecular chemistry as a chemistry beyond the molecule or chemistry of the non-covalent bond. Okay, and if you assume that this is one covalent molecule and this is another covalent molecule, and if these two molecules if they possess a complementary binding site, what will happen? They will self-recognize each other with respect to their functionality present, and they will be embedded within this large macromolecule. Okay, and this interaction is mainly driven by the non-covalent interaction. So the study of any molecule which are formed through non-covalent interaction are considered as a supramolecular chemistry, and this particular structure we consider as a supramolecule. In other words, we can also call it as a host-guest complex, because this is acting as a potential host, and within that this green circle type of molecule goes, square type of molecule fit into this cavity through non-covalent interaction. Okay, so study of this type of molecule comes under supramolecular chemistry. Now you may be wondering that what is the beginning of supramolecular chemistry, where from it started. So as I said, the molecular chemistry, you can say that the beginning is when the urea was synthesized by Wooler in the year 1828. On the other hand, supramolecular chemistry beginning is through an accidental discovery by Charles Pedersen. So Charles Pedersen, who is also one of the Nobel laureate, but he did not get a formal PhD degree. And he took a master degree in MTech in chemical engineering from MIT. After that, due to the personal reason, he joined in an industry called DuPont Chemical. Now, DuPont Chemical is renamed as a Dow Chemical. Dow Chemical is one of the very famous manufacturing chemical industry in USA. And so he joined after the master degree from MIT. He joined as a technical person or synthetic chemist in that particular unit. And at the time, in the early 1950s, the DuPont Chemical was mainly interested in making petrochemical product. Okay, so when they were making petrochemical product, they found the petrochemical product mainly they were synthesizing with the help of metal-based catalytic process. After the isolation of the petrochemical product, they found the trace quantity of vanadium and copper metal ion mixed with the final product. Okay, so when you have such a trace quantity of transition metal ion, they will auto-oxidize the final product, particularly the petrochemical product, and the industry were losing their product. Okay, so mean their profit. So they were not able to make the huge profit out of that petrochemical product because of that auto-oxidation that happened due to the trace impurity that present in the final product. That impurities are vanadium and copper. And at the time, Charles Pedersen, he was one of the well-experienced synthetic chemist working in that industry, and the industry people asked him that can you make a scavenger for this metal ion so that we will be able to overcome the auto-oxidation process, and finally we will be able to make the product. The experienced Charles Pedersen set out to synthesize metal scavenger. He wanted to actually make this particular linear diol and then subsequently use it as a metal scavenger. Okay, to synthesize this molecule, he started actually initially from this monoprotected catechol, and he reacted in 1:2 stoichiometry ratio with bis-chloroethoxyethane in presence of sodium hydroxide in the first step, and the second step was the acidic protonation. Okay, acid-based protonation, and that resulted in the expected linear diol as major product. During the synthesis, he also observed a tiny product which was highly crystalline and highly crystalline product, which he isolated only in 0.4% yield. And curious Pedersen did not throw that side product which he isolated in 0.4% yield. Rather, he started to analyze what might be that particular product. Okay, so early 1960s, we did not have that much sophisticated instrument as we have now. So he decided to use whatever the technique that time available in early 1960s. And two interesting observations he noticed. One is when he took this side product and put it in methanol, as such, the solubility was not that high. Okay, but when he added a trace quantity of potassium, he found that the solubility was enhanced drastically. The whole side product was completely went into the solution. That was one interesting observation. And the second interesting observation was he found that the molecular weight of the side product was almost twice the molecular weight of this major product. Okay, so these two observations made him to understand what might be the exact structure, and then he used further few other technique to understand the overall structure, and based on his finding, he proposed that the side product that he observed along with this major product is nothing but the dibenzo 18-crown-6. And this dibenzo 18-crown-6, when you propose that this might be the product, you have to give a reason why this particular product is forming. Now, in order to find out the reason, he went back to the starting material that he was using to make this major product, and he found that a trace quantity of catechol. Okay, so this monoprotected catechol, which he prepared from the catechol, and he monoprotected and subsequently reacted with this bis chloro ethoxyethane to produce this linear dia. The trace quantity, whatever is present in this particular system, that stoichiometrically react with this bis chloroethyl ethane, and that result in the formation of this ground ether. Okay, and he named this as a dibenzo 18 ground 6 because there are 2 phenyl groups and there are 18 atom in the cycle and 6 oxygen atom present. That's why it's called dibenzo 18 ground 6, which he isolated only in 0.4% E. Now he also tried to find out that the reason why it was highly soluble in presence of potassium. Why? Because the 18 ground 6, it acts as a host molecule where the cavity size perfectly fit with ionic radius of potassium ion, and that results in the stable host complex formation. So through ion dipole type of interaction with a lone pair of electron on the oxygen and with a positive metal cation, and that made this overall system fully soluble in methanolic solution. And the molecular weight, he found that it is a dimeric form of this major product. Okay, so in fact the beginning of supramolecular chemistry or the modern supramolecular chemistry started from this particular accidental discovery, which he isolated only in 0.4% E. Subsequently, there were many research teams, they were working on making such a cyclic structure. Professor James learned from University of Strasbourg, France. He started to make a 3-dimensional structure. The ground ether is a 2D structure, and he started to make a ground ether type 3-dimensional structure, which he named as a krypton. The 222 mean there are the number of oxygen atom in each linkage. Okay, so here there are 3 linkage, and each linkage has a 2 oxygen atom, and that results in the 222 kryptons. And he made a series of 3D kryptons, and he found that the same way how the 18 crown 6 form selective complex with the potassium ion, this krypton also form a selective complex with the potassium ion through this ion dipole type of interaction. Why it is also forming a selective complex with the potassium? Because though it's a 3-dimensional structure, but the cavity size and the number of oxygen atom present in this structure is matches with the 18 crown 6. Okay. Similarly, Professor Donald Graham from University of California, USA, he started to make a rigid macrocyclic structure that he named it as a cavidin or spherent. And this is one such an example where you can see that almost 6 phenyl groups are connected in a cyclic manner, and there are methoxy group which are directed inwards. And if you look at that, here also there are 6 oxygen atoms, but if you look at the cavity size, which is much smaller than the 18 crown 6 and the krypton. Okay, so because the cavity size is very small, it could not form a selective complex with the potassium, rather it forms a selective complex with the lithium ion. Okay, so for their development and use of molecule with structure specific interaction with a high selectivity, and these 3 scientists were awarded Nobel Prize jointly in the year 1987 in chemistry. Okay, so among these 3 Nobel laureates, Charles Pedersen, he was just a master degree holder from MIT, and the other 2 are academician, and they were having a formal PhD degree. Okay, so this slide shows the curiosity of Charles Pedersen. He did not throw that 0.4% yield, and that he analyzed, and finally he could able to isolate this 18 crown 6 and understand the structure specific interaction, and that resulted in a Nobel Prize in chemistry for him. Okay, and subsequently in another within 2 years of the Nobel Prize was awarded, and Professor A.P.D. Silva, he is basically from Sri Lanka, but he is a senior professor working in Queen's University, Belfast, UK, and he is my academic grandfather because he was a supervisor of my postdoc supervisor, so I always call him as my academic grandfather. So within 2 years of this Nobel Prize was awarded to 3 gentlemen in supramolecular chemistry, and A.P.D. Silva, he wanted to develop something useful out of this discovery. Okay, so what he did was he took this 15 ground 5, and one side he connected with anthracene, which is a fluorescent unit, and the other side of the anthracene he introduced this quaternary ammonium salt. The reason why he introduced the quaternary ammonium salt to make it water soluble. If you are making anything practically useful, it is always preferable to have systems which are water soluble. To make this system water soluble, he introduced this quaternary ammonium salt, and whereas this anthracene mighty is acting as a signaling unit, and this 15 crown 5 acting as a receptor site to form a host space complex. Okay. Now, if you look at this molecule as such, and if you shine the light on this molecule, there will be a photo-induced electron transfer that happened from the lone pair of electron on oxygen atom to this anthracene pi star orbital. So, because of this photo-induced electron transfer, the overall structure is non-emissive. Okay. Now, upon interacting with the metal ion, and here it's not 18 crown 6, it's a 15 crown 5, and because of that, it's not forming a complex with the potassium, rather it forms a complex with Na plus ion. So, when upon binding with the Na plus ion, the lone pair of electron is already in a connection with metal ion, so it is no more available for this photo-induced electron transfer process. So, because there is a switching off of this PET process, and he started to see the strong emission that is coming from the pi to pi star transition of the signaling anthracene unit. Okay. Now, the fluorescent enhancement or signaling of fluorescent unit depends on this concentration of the amount of sodium ion that we mix it during the experiment. By reciprocating the total amount of concentration of Na plus with respect to the emission that is coming from anthracene, one can easily quantify the amount of sodium ion present in the system. So, he published this particular work in chemical communication in the year 1989 after 2 years of Nobel Prize that was awarded in 1987. But Professor A.P. De Silva did not stop after publishing this work. He was very curious, why can't we make it so practically useful for something to society. Okay. So, he wanted to actually make it as a real-time application of this particular system. What he did was he made a kind of a cassette, okay, or a device with the help of different granular based such a molecule. He kept all these units constant, and he just tuned the cavity size of this ground ether starting from 15 crown 5 to 18 crown 6 and even bigger ground ether, so that the bigger size alkaline earth metal ion also can be incorporated within it. Okay. So, after making a series of molecule with a different ground ether, he made this particular cassette which he is holding in his hand here, and each spot is corresponding to one particular compound with a different ground ether. Okay. And each ground ether is specific for one particular metal cation, and this particular cassette was used to quantify the electrolytes present in the blood sample. Now, if you see that this particular cassette is currently being used in most of the developed country in intensive care unit and as well as in the ambulance service, and to instantaneously find out the electrolytes present in the blood sample. So, how this the electrolyte concentration one can determine using this particular cassette is that you take the blood sample and put it inside this tube, and there is actually capillary that pass through all this part. Okay. So, it is actually almost colorless, but there is a U-shaped capillary. Once you put the blood sample here, that blood touches all this spot, and once it reaches here and put it in this readout box, and instantaneously you will get the amount of electrolytes present in your blood sample. Okay. So, currently this technology is being sold by this Opti Medical and IDEX laboratory. These are the two industries who are manufacturing and selling it for this intensive care unit. Okay. And so, you can see that the total sales of this particular cassette so far, which is almost $540 million US up to 2018. So, I don't know the current value, how much it is being sold. Up to 2018, this particular cassette was sold for almost $540 million US. You can see that a simple discovery of chemical sensor to quantify the electrolytes present in the blood sample, and that resulted in the formation of in the development of such a technology, and that is being currently used in many European countries and the USA, and you can make a huge profit out of it. Okay. And since 1990, you can find that there are many research groups, they were interested to make such a cyclic structure, start from cyclodextrin, calyxarin, cyclophane, octoacids, curcubitril, ground ether, fullerene, and pillarine. These are all many different organic host molecules that were reported by many different research groups. But one disadvantage with this particular system is that all these organic macrocycles were synthesized by the traditional covalent synthesis. What is a traditional covalent synthesis? CC bond forming and breaking reaction. Okay, so if you want to make such a large macromolecule through CC bond forming reaction, it requires multi-step reaction. Okay, so you cannot make it in a single step. You have to adopt multi-step reaction. When you adopt a multi-step reaction, it always leads to time-consuming process, and the final product ends in the low yield low yield. Okay, because where each step you have to isolate the product and purify them, and subsequently use it in the subsequent reactions. So when you adopt multi-step reaction, it's a time-taking process, a tedious process, and laborious. Always ends in the low yield of the final product. Okay, and late 90s, people started to look for an alternative synthetic tool. Why can't we use something alternative to this traditional covalent synthesis? So as usual, so before that, let me just tell you with one example how difficult difficult to make this large organic host molecule. For example, fullerene C60, which was reported by Scott et al. In the year 2004, which he synthesized starting from this chlorobromoethane. It required almost 12 steps, and after 12 steps, you can see that the final product, which he isolated only in 0.1 to 1% yield. So you put so much of energy, so much of money, and so much of chemical, and do the multi-step reaction, and finally you get the final product in only 0.1 to 1% yield. That is happening only because you are adapting the stepwise covalent synthesis of making this fullerene C60. Now, people started to look for an alternative synthetic method to make this large macrocyclic compound. As usual, nature always inspires us by its elegant synthetic procedure as well as their beautiful biochemical functions. So one such example is the DNA double helical structure. I'm sure that all of you know that the DNA double helical structure, how this is forming. You can see that the DNA double helical structure is originally formed because of the intermolecular hydrogen bonding interaction between the nucleobases. So where you can specifically look at the guanine forms selective hydrogen bonding interaction with the cytosine, there will be 3 intermolecular hydrogen bonding. Similarly, adenine selectively form a 2 hydrogen bonding interaction with the thymine. So because of this multiple hydrogen bonding interaction, this DNA double helical structure is stabilized. So basically, this hydrogen bonding interaction is non-covalent in nature. So here comes the interesting observation by many scientists that why can't we use the nature non-covalent synthetic procedure to make such a large macromolecule instead of the traditional covalent synthesis. Okay, so that here comes the beginning of supramolecular self-assembly strategy instead of the traditional covalent chemistry. So let me tell you what is supramolecular self-assembly. Before that, what is self-assembly? Self-assembly is nothing but a spontaneous association of 2 or more building units which are combined together non-covalently that results in a well-organized structure. Okay, so that's a well-organized structure. We call it as a supramolecule, and the driving force that happen through non-covalent interaction. So the overall process we consider as a supramolecular self-assembly. To make you all understand, here I have given a cartoon representation. For example, you consider these 4 different objects having a different shape, different size, and different colors, and assume that the color is a different functionality. If you allow them to react through non-covalent interaction or through the self-assembly process, they will self-recognize each other depending on their shape, size, and that will result in well-organized this type of triangular structure. Okay, and this overall process we consider as a supramolecular self-assembly. Now you may be wondering that what are the advantages of having supramolecular self-assembly over the traditional conventional covalent synthesis. So as I said, that conventional covalent synthesis is a multi-step reaction. It takes a time-taking process, laborious, and always ends in the low yield of the final product. On the other hand, if you look at the supramolecular self-assembly, it is a one-part synthetic process, and hence time-saving and it's less laborious compared to the traditional covalent synthesis. And since it's a one-part synthetic procedure, we can isolate the final product in quantitative yield. And added advantage here is that when you take a building block, they will assemble and disassemble dynamically until the thermodynamically stable product is going to form. Okay, so because of this thermodynamic stability, one can isolate the targeted final product which are self-healed, which means there won't be any defect in the final structure. That is mainly because of their assembly and disassembly process. For example, you look at this figure. If you allow these two objects to react covalently, you may end up getting a unexpected or unwanted product. Whereas if you allow them to react through non-covalent self-assembly process, they will assemble and disassemble through non-covalent interaction until it forms a self-corrected final product. So now this assembly and disassembly process are mainly driven by the non-covalent interaction, and there are many non-covalent interactions that we have come across. But whenever we choose a non-covalent interaction to design a large macromolecule, there are two things which we need to consider. One is the strength of the interchemical interaction. Second is whether it's a directional or non-directional. Why these two parameters are very important? The strength is very crucial because when you take a building block, allow them to react non-covalently, you isolate the product. In case if the strength of that particular chemical interaction, if it is very weak, then the final product will not be stable, it will go back to the starting precursor. Okay, so that means we need to have a moderate bond enthalpy so that we will be able to isolate the final product and then subsequently use it for the various applications. And the second important point is whether it's a directional or non-directional. Why it is important? For example, you take two building blocks. You are interested to make a kind of square type of molecule. So each corner is 90 degree, and that will be connected with a 180 degree complementary donor or acceptor. So if the binding side, if they are non-directional, then you may get the unwanted product or polymeric product. Okay, if it is non-directional. Okay, so whenever we take a non-covalent interaction, the bond strength should be moderate. At the same time, the bonding interaction should be highly directional so that we can able to control the product formation. Okay, there are many different type of supramolecular interaction. So here I will be highlighting the advantage and disadvantage of a few supramolecular interaction. So the first one is ion-ion interaction. So one best example is the sodium chloride, and if you look at the strength, the chemical strength of this ion-ion interaction, which is almost 25 to 100 kilocalories per mole, which is too high, and also it's comparable to covalent bond strength, and it's non-directional, non-specific. Okay, so that means it's not matching with the two of our expectation. The bond should not be very strong, otherwise it will result in the irreversible unwanted product. At the same time, if it is non-directional, you may not get the expected product. So ion-ion interaction doesn't match with our expectation, so we cannot use ion-ion interaction for self-assembly process. Next is ion dipole interaction. So where you can see the bond strength is 10 to 50 kilocalories per mole, and it's less than the covalent bond, and there exist elements of directionality. There is a directionality, but bond strength is much weaker than the covalent bond, and because of that you may not be able to get this the self-assembled final structure if you use ion dipole as a primary chemical interaction to make a supramolecular structure. But in this case, it is forming just a host case complexes. It is fine, perfectly fit into the cavity through multiple ion dipole interaction. This potassium ion is getting stabilized. But if you use potassium as one of the building blocks to make a large macromolecule, that macromolecule will not be stable supramolecular structure because of their weak interaction. The next interesting one is a dipole-dipole type of interaction. For example, this is a myrocyanine di molecule. It has a dipole, and that dipole is almost 17 dBi. So the dBi is a unit of the dipole moment. So you can see that the 17 dBi. So that means one side is acting as a donor, the other side is acting as a acceptor. And if you allow this donor acceptor unique molecule, and they will form this type of dimeric structure by stacking interaction between the donor and acceptor, and this is through the non-covalent dipole-dipole interaction. The strength is almost 1 to 15 kilocalories per mole. This is much weaker than the covalent bond, but still there exists an element of multiple directionality. Though there is a directionality, but due to the weaker chemical interaction, and this particular dipole-dipole interaction cannot be used as a primary interaction or chemical force to make a large macromolecule. Next is a pi-pi stacking interaction. Again, the same problem. The chemical force is very weak, and there are many different geometry possible with the benzene. As such, we cannot get the expected geometry. Okay, and then cation pi interaction, strength is very weak, and there is a possibility to have a different type of geometry which may not be the expected structure. Okay, so again the cation pi interaction also cannot be used. Now, if you come to hydrogen bonding interaction, if there exists a multiple hydrogen bonding interaction simultaneously, you can able to isolate the final product, as we have seen in the DNA double helical structure. If there is only one interaction in DNA double helix, that structure will not be stabilized. The structure is stabilized because of these 5 intermolecular hydrogen bonding interaction. Though the chemical strength is only 5 to 15 kilocalories per mole and weaker than covalent bond, but because of this multiple hydrogen bonding interaction, we can also use the hydrogen bonding interaction as a driving force to design a large macromolecule. But if you consider metal-ligand coordination interaction, if you look at the hydrogen bond, the bond strength of metal-ligand bond, which is 15 to 50 kilocalories per mole, which is a moderate bond strength and is a highly directional. If it is highly directional, very easy to control the reactive reacting building block, and then we can isolate the final product, the expected geometry. And we know that we have a beautiful periodic table. We can select any kinds of metal ion of our interest. For example, if I want to make redox active supramolecular structure, I can select the redox active metal ion, for example, ruthenium and iron. And if you wanted to make a photoactive system, you can select a platinum or other luminescent metal, and then we can use those metal to make a large macromolecular structure. So all these interesting property make the metal-ligand coordination interaction as a primary interaction as well as an excellent candidate to for supramolecular self-assembly and to make a large macromolecular structure. We can also introduce multiple functionality by fine-tuning the reacting building blocks. So hereafter I will be focusing how we can use metal-ligand coordination interaction as the driving force to design a large macromolecule. Okay, so whenever we talk about the coordination bond, we need a metal-based acceptor and organic donor. Okay, so to make you all understand that I will here I have given what is 90-degree acceptor. Before that, we are particularly our group, we are not interested in using all type of metal ion. We are particularly interested with the platinum and palladium based metal center. Why? Because palladium platinum form a very stable square planar geometry and their kinetic level nature. So kinetic levelity is very important when the assembly and disassembly process take place. Okay, so because of these two interesting property, we are particularly interested in using platinum and palladium based supramolecular building block and to design a large macromolecule. So if you look at this platinum complex, among 4 coordination sites, I have blocked 2 sites with ethylene diamine in order to limit the number of possible coordination sites, and the other 2 sites are occupied with a better leaving group nitrate. So when you take this 90-degree acceptor and allow them to react with the donor molecule will approach the metal center by displacing this better leaving group simultaneously. So if you look at the angle between these 2 nitrate, which is 90 degrees, so we call this as a 90-degree cis block because these 2 sides are blocked with ethylene diamine. So 90 degrees cis blocked acceptor because it's accepting the electron. Similarly, we can also synthesize a series of shape selective acceptor by selecting the appropriate organic building block. For example, here the angle between their 2 platinum is 0 because they are parallelly oriented, and here it is 60 degree, and again this also this is 120 degree and this is 180 degree. Okay, so we can design a building block metal based acceptors with a different bite angle. Now once you are ready with acceptor, the next question is a donor. As you all know, donor is a chemical composite which donate a pair of electron to form a chemical coordination bond, and bite angle is nothing but the angle between the 2 donating and accepting side. Okay, so here it is a 60 degree donor where you can take, if you look at the lone pair of electron on each nitrogen, and it's 60 degrees, so we call it as a 60 degree donor. And similarly, we can also make a 0 degree, 90 degree, and 120 and 180 degree acceptor. So once you are ready with the donor and acceptor, next is what type of molecule we are going to make it. Okay. So for that, we will try to refer this molecular library, which is actually a reference chart for us for supramolecular chemistry. For example, if you are interested to make a 2+2 molecular square, the best combination will be you take a 90 degree acceptor and stoichiometrically combine with a 90 degree donor. That will result in a quantitative formation of 2+2 molecular square. Similarly, you take a 90 degree, a 60 degree acceptor and react with a 180 degree donor, and this combination will result in the molecular triangle formation. Okay. So in the same way, we can also design all the other 2D structure by selecting the appropriate building block having the proper bite angle. If you want to make a 3D supramolecular structure, one important point is that among two reacting building block, acceptor and donor, one of the building unit must have more than 2 reactive sites, so that it will result in a 3-dimensional structure. For example, if you are interested in making trigonal bipyramidal structure, the best combination is going to be a tritopic 60 degree acceptor and 109 109 degree ditopic acceptor and donor. So this combination will result in the trigonal bipyramidal structure. We can also design this intricate supramolecular structure by selecting the appropriate building blocks. So far I have introduced what is supramolecular chemistry and what is a non-covalent interaction and what is a molecular self-assembly strategy, how it is different from the traditional conventional synthesis, how we can use the metal-ligand coordination bond, and hereafter I will explain to you how we have used this metal-ligand coordination as a driving force for making a supramolecular structure, including their application. The first example, in fact, this is very first molecule which I prepared in my PhD. Okay, when I started my PhD, the first molecule which I prepared was this diplatinum 90 degree acceptor. That's why I always interested to show this as a best example. So if you look at the angle between these two platinum, nitrogen, platinum, which is a 90 degree. So though it is a diplatinum metal center, but the angle between the two reactive sites is 90 degree. Okay. When we took this 90 degree acceptor and reacted with this flexible dipretyl donor in acetone at 50 degrees centigrade, after 5 hours of stirring, we found the formation of a molecular square. And this is a single crystal X-ray structure of molecular square. And if you carefully look at the molecular square, it is composed of amide-based receptor and carbazole-based luminescent moiety. Okay, and amide is very well known to form hydrogen bonding interaction with various anions, and carbazole is known to show strong fluorescent behavior because of the strong pi to pi star transition. So because of this high emission and receptor sites are present, we naturally thought that why can't we use it as a sensor for various anions? And we, for our studies, we took only 4 different anions like perchlorate, F- and dihydrogen phosphate and pyrophosphate. And when we did this sensing study with the help of fluorescence, we used a fluorescent technique to monitor their interaction with the molecular square, and we found a strong enhancement in the fluorescent intensity when we added pyrophosphate, whereas other oxoanion did not show any such a strong emission intensity. Same with the fluorine also. So you can see this is a gradual fluorescent titration where this is the initial emission that is coming from the molecular square, and after adding the pyrophosphate, we can clearly see there was a gradual increase in the emission intensity, and we calculated the binding constant from the Stern-Normer binding equation, and that is almost in the order of 10^4. So this indicates that this particular molecular square can be used selectively for pyrophosphate as a scavenger. Now you may be wondering that why it is selectively forming a complex with the pyrophosphate, because if you look at other oxoanions or halide, they are all small in size. So they may not fit perfectly with this cavity to form a non-covalent interaction, whereas this pyrophosphate is larger in size because it's a P2O4 4-, that perfectly snugged within this cavity, and that results in the strong interaction between the pyrophosphate and molecular receptor, and that shows a strong fluorescent enhancement compared to all the other oxoanions. in a complementary approach. So here it's a carbazole based acceptor and this is a dipyridyl donor. In a complementary way, I designed the carbazole based dipyridyl donor. Again, it's a 90-degree dipyridyl donor and reacted with this palladium based 90-degree acceptor. Okay. So when we mixed these two, we anticipated that it will also result in the molecular square, but to our surprise, we found that it resulted in the formation of molecular bowl-shaped structure, where you can see that it is like you hold two hands in the way in this way. It's like a bowl-shaped structure, and it is filled with the pi electron rich carbazole unit. And we thought that why can't we use this as a potential host? And one possible or one interesting guest molecule is a fluorine C60 because it's one of the largest convex guest molecule, and this is having a concave cavity. So they may complementary recognize each other and form a strong pi-pi stacking interaction. As we anticipated that this particular molecular bowl form a strong host-gas complex with the fluorine C60, and then this was also reflected from the fluorescent titration, where we can see that initial emission of this molecular bowl is decreased significantly upon increasing the concentration of fluorine C60. And when we calculated the binding constant, which is in the order of 10 power 5 per molar. So this was published in inorganic chemistry, and the previous work was published in organometallics. Now, next interesting example is white phosphorus. I'm sure that many of you are aware about the white phosphorus. It's not a very friendly molecule. It catches fire when it exposed to the atmospheric oxygen. The reason why it catches fire, because if you see the white phosphorus, when it exposed to the oxygen, the product what is going to form is a P4O10, and upon interacting with the water, the P4O10 convert into phosphoric acid. If you look at the phosphorus bond energy here, which is a 200 kilojoule per mole, whereas in the product, phosphorus oxygen bond is much stronger, which is 330 to 650 kilojoule per mole. So the product is stronger, having a stronger chemical force than the reactant. So that means the activation barrier going to be very, very low for this particular reaction. That's why the white phosphorus is highly reactive when it is exposed to the atmospheric oxygen. Okay, and the P4 it ignites spontaneously upon contacting with the air and quickly decompose into phosphorus 5 oxide by releasing substantial amount of energy. So because of that, we consider white phosphorus as highly flammable or pyrophoric in nature. Pyrophoric means any compound which is easily catch fire. Okay. Now, one of the scientists from Cambridge University, he was very much interested to stabilize reactive species. So white phosphorus is a reactive species. We have to stabilize it within this supramolecular structure. So the logic that he used to stabilize this white phosphorus was very simple. You know that lion, which is very furious in the forest, which is a very furious wild animal. In the forest, we may not be able to control the anger of this lion, but once you put them inside the cage, we can able to control them. So outside the cage, we have to listen to them, but once you put them inside the cage, they will listen to you. Okay, so this is a very simple logic that he used to stabilize this white phosphorus, which is a very reactive species. So white phosphorus is a tetrahedral structure, and we also know the diameter of the white phosphorus. Now he designed a tetragonal prismatic structure, the tetrahedral capsule, having a complementary geometry. At the same time, the cavity perfectly fit for the white phosphorus to go inside. So this was synthesized by the self-assembly reaction of this aldehyde, amine, and in the presence of FeSO4, and that resulted in the tetrahedral cage-like structure. And this tetrahedral cage-like structure formed a very selective complex with the white phosphorus. Okay, so once the host case complex was forming a white phosphorus between the tetrahedral structure with the white phosphorus, and then this host case complex was monitored with the help of phosphorus NMR. When he took the white phosphorus NMR within the cage, he found that minus 510 ppm. Okay, so that is corresponding to the phosphorus stuck within this internal cavity. So once it forms a host case complexes, he also tested whether it is decomposes into P4O10, and he found that this white phosphorus was highly stabilized within the cage, and there is no conversion of white phosphorus to B4O10, or no leakage of white phosphorus, or no formation of phosphoric acid. You may be wondering that what is happening once it goes inside. So once it goes inside, it is highly stabilized. How it is stabilized? Why even in the presence of atmospheric oxygen, why it is not converting into B4O10? Because if you look at the size of B4O10, which is much larger compared to white phosphorus. So Jonathan Mitzke, he was very clever in designing this tetrahedral cage-like structure. He designed the tetrahedral cage whose size perfectly matches only with the starting material, not with the product. So in order to accommodate the product, the cavity size should be large enough so that, because the product size is larger than the white phosphorus, but this particular cage doesn't have that much large internal cavity to accommodate the product. So the conversion of white phosphorus to B4O10 within the cage, then activation barrier is now high. So it cannot easily cross this activation barrier. Because of that, this white phosphorus gets stabilized within this tetrahedral cage. Now, in addition to the stabilization of the white phosphorus, he also demonstrated the releasing of white phosphorus by introducing the competing analyte. So in a separate study, he found that in addition to white phosphorus, this particular tetrahedral structure also strongly form a complex with benzene, and he layered benzene. He took a test tube with white phosphorus and the tetrahedral host phase complex in water. Nothing happens, and he layered benzene, and after shaking, the benzene slowly goes inside because the tetrahedral cage has a preferential binding for benzene because of the pi-pi stacking interaction. So the benzene gradually goes in and kick out white phosphorus, and once the white phosphorus comes out, it exposed to the dissolved oxygen, also to the water molecule, and then finally you convert it into phosphoric acid. Okay, so once it is inside the cage, white phosphorus stable as such, but once it is come out, that it can finally convert into phosphoric acid. This was also monitored with the help of phosphorus enema. The P4 in benzene layer, which is minus 510 20 ppm, whereas the white phosphorus within the cage, it is a minus 510 ppm. So why this 10 ppm difference is coming? Because of the confinement effect that is coming from this internal cavity, and once it converts into white phosphorus, it becomes 0 ppm, because white phosphorus is a standard for phosphorus element. So this technology can be adapted for environmental sequestration, where we can design a cage-like structure to selectively form a complex with the geogenic or anthropogenic pollutant, and then later we can also release them from the cage. So this is a new technology that can be adapted for various environment or hazardous related issues. So the chemistry is very simple, but if you look at the journal where this work was published, this was published in Science. So the idea was this very simple logic, okay, but the curiosity that gave him the science paper. And another one interesting paper that came from Makoto Fujita from Tokyo University is that can we use the molecular supramolecular structure as a molecular flask or molecular reaction vessel. So if you look at the conventional Diels-Alder reaction, you take a dienophile. If you allow them to react, the only product that we will be isolating is a 910 adduct. Okay, so why it selectively formed 910 adduct? Because this resonance conjugation leads to more pi electrons at this 910 position, and the immediate reaction that's going to happen is a 910 adduct formation. So in order to modulate the reactivity of this 910 adduct, Makoto Fujita from University of Tokyo, he synthesized this octahedral cage-like structure by combining the 90-degree acceptor with a tritopic donor, where this is a pyridyl rigid tritopic donor that resulted in a large M6L4 molecular cage. That means 6 unit of acceptor, 4 unit of this donor molecule in water, that resulted in the formation of this cage-like structure, and this cage is fully water soluble because of the positive charge, 12 positive charge. Now once he synthesized, he started to analyze whether we can able to use this as a potential host molecule to modulate the reactivity of the conventional Diels-Alder reaction. He took a dienophile along with the host molecule in D2O, and it forms a very stable host phase complexes because of the strong pi-pi stacking interaction. And upon heating at 80 degrees centigrade, and he found very unusual side product, very unusual product formation, that is a SYN-1,4 adduct formation. Stereochemically or regiochemically, if you can see the product, it is completely unusual regioselective product. So this type of unusual product is not possible without the cage-like structure, we always get the only 910 attack. So he was fortunate that he could get the X-ray structure to understand the reason why it is forming 1,4 adduct, that is even specifically 1,4 adduct, not the trans 1,4 adduct. So you can see that the crystal structure of the Hotchkiss complex, because of this confined cavity, the diene and dienophile, they are placed in such a way that the 1,4 position is very close to this dienophile. Okay, so because of that, once you shine the once you heat up the sample, the immediate reaction that's going to happen is the 1,4 adduct, and that is the syn 1,4 adduct, not the trans 1,4 adduct, because to form a trans 1,4 adduct, the cavity size should be large enough to accommodate. Okay, so he also introduced a different bulky group, and he found that wherever there is a bulky group, the final product yield was actually increasing as we move from ethylene to cyano to carboxylic acid. Okay, so this is also again it's a very simple observation, and this was published in Science by Makoto Fujita. So during my PhD, we were also interested to see, can we also make such a macrocyclic host molecule and study the Diels-Alder reaction? What will happen if we replace the rigid tripodal donor? So basically, this rigid tripodal donor we replaced with flexible triimidazole donor. Okay, but excuse me. So so we used exactly the same 90-degree acceptor, but we used a flexible tritopic donor. Yeah, sorry. So when we mixed this donor and acceptor in water at room temperature, after 24 hours, we isolated an unusual structure which is different from this octahedral cage-like structure. We didn't expect that it will form this type of open cage-like structure. This is a single crystal X-ray structure. It has a large opening. So I forgot to mention here that one drawback of this particular system is that it's a stoichiometry, not a catalytic reaction, which means in order to get the one equivalent of the final product, you need to have one equivalent of the cage-like structure, because the cavity portal is not large enough to release the final product. So if you want to release the product, you have to break the cage. So one equivalent of cage will convert one equivalent of starting material into product. But our curiosity is to make a catalytically active supramolecular cage-like structure, and as we anticipated that we isolated a cage with a open cavity, and in fact this we didn't expect, but we were expecting the cavity should be large enough because of this ligand flexibility. And then we carried out the same Diels-Alder reaction with the diene and dienophile. Without the cage, we found that the 910 adduct formation almost in 11% yield, but in presence of cage, again we got only 9,4 adduct, but it's almost 90% yield. You may be wondering that why it is not forming a 1,4 syn adduct, because the cavity size is large enough that it's not actually allowing, it's not giving any restriction or confinement due to the confinement due to the internal cavity. So here the internal cavity is large enough, and that allow this molecule to form only the 910 product, not the syn 1,4 adduct. But one advantage what we observed, the catalytic activity, which is almost 90%, and this is catalytically active product. This is a catalytic loop or cycle where you take the open cage, put diene dienophile, they are stabilized with the pi stacking interaction. Upon heating, it forms a 910 adduct, and so once it forms a 910 adduct, it comes out of this cage. Why it comes out of the cage? Because there is no more pi stacking interaction because of this deformation that is happening with the product. So that resulted in the formation of 910 adduct. So we were able to isolate a open cage-like structure which are catalytically active, but we failed to get the syn 1,4 adduct product formation. But in their case, one drawback is that is stoichiometry, not catalytic. Okay. So whenever we do some chemistry, there will be always some kind of advantage, some limitations. So we always, as a researcher, we always need to look for a new method or new strategy to overcome overcome those limitations. So this is one aspect. Another aspect of different application is how we can use these metal cages as a luminescent sensor for chemical explosives. You know, nitroaromatic, TNT and picric acid, these are all secondary chemical explosives, and they have been used extensively as a chemical explosive because of their inexpensive synthesis from the starting material and easy transportation. So you can make a TNT picric acid from inexpensive starting material by simple nitration reaction, and we can also easily transport. Whenever people make a hazardous material or explosive material, transporting from one place to the place where it's going to be detonated, it's going to be dangerous if it is highly reactive. Okay, but in the case of TNT and picric acid, since they are secondary chemical explosives, they are easy to transport. And one of the commercially available nitroaromatic explosives is the tritonol, which is nothing but the mixture of 80% TNT and 20% aluminum powder. Okay, so the aluminum powder is required as an initiator to detonate TNT because this is secondary chemical explosive, whereas RDX is a primary explosive, doesn't require any initiator. So apart from their chemical explosive property, picric acid, which is a very bright yellow pigment, and it has been used as a yellow dye molecule in leather and dye industry as a yellow pigment. Okay, so apart from their chemical explosive nature, there are several health related issues when we expose to the vapors of this nitroaromatic compound. For example, if you expose for a shorter duration to the vapors of TNT and picric acid, that leads to cataract and severe headache, and long-term exposure to this chemical explosive results in the anemia or
anemia. Sorry for the interruption, sir. Excuse me, sir. Yeah. Sir, we have 10 more minutes, sir, so that we can have discussions later.
I'll finish in 10. Yes.
Yeah, okay. Thank you, sir. Okay. Yeah, thank you, sir.
So anemia, and then we can also see the neurological damages. As per the EPA, Environmental Protection Agency, the permissible concentration of TNT picric acid, which is 2 nanogram per ml, and beyond this limit, which is considered as a toxic one, we design a tetragonal prismatic structure and used as a sensor for various chemical explosive, particularly for the secondary chemical explosive. We used this pyrene based tetra platinum acceptor. We made this tetragonal prismatic structure, and we used a fluorescent technique to monitor their binding interaction. We could see that it selectively binds with the TNT and picric acid with subsequent with substantial fluorescent quenching effect. We can also see this sensing process in the solid state. We made a thin film and we exposed to the vapors of nitroaromatic compound. We could see that significant quenching effect. And in subsequently, we made a inorganic polymer to do the same process. We took this tetracarboxylic acid using this Troger base unit, where there is a ICT process that is happening from the lone pair of electron, the nitrogen, to this pi star to the imide side, that make this compound highly fluorescent. And we made this infinite coordination polymer, and we found that the polymer is highly fluorescent compared to the starting material and shows a strong binding affinity towards the picric acid. And this is a visual color change that we have observed, a strong fluorescent to almost non-fluorescent upon adding picric acid. And we also proved the mechanism as a static dynamic quenching mechanism, because we found that there is a change in the lifetime upon increasing the concentration of picric acid. And then it was a very quick sensor. Within a minute, we could see almost 90% quenching effect. And one interesting observation here is that we can reverse the sensing process. This is the number of reversible cycles that we observed with this particular infinite coordination polymer. So this is another one example in continuation to this nitroaromatic compound. This is purely organic polymer. We cyclize this amine into Troger base containing organic polymer. This is scanning electron microscope image, shows a highly porous structure, and we characterize using the solid state NMR and FTIR. And since it's highly porous, we thought, why can't we use this as absorbent? And we use a UV visible absorption as a tool to monitor this absorption process. When we take the 3 milligram of polymer, put it in picric acid, we could see with respect to time the intensity of absorption intensity of picric acid gradually decreases. And we could also do this absorption and desorption process for many cycles. And this is a visual color change. You take a picric acid, put 3 milligram of polymer, we can see that completely absorbed. And this absorption can be reversed by fine tuning the pH of the medium. Okay. So this is another one interesting example we recently published, where we made this nitrogen-rich organic polymer, and this polymer we found that it shows a discriminative fluorescence sensing towards a volatile organic compound in particular for the 1,4-dioxane and tetrahydrofuran. So we can see that the 1,4-dioxane shows almost 44 times fluorescent enhancement when we compare the emission of this particular polymer in water. Okay, and this was also studied in solid state, where we can make a thin film. This is a ACM image of the thin film of this polymer, and we can expose to the vapors of this volatile organic compound, which are hazardous in nature, and we could see that there is a color change as well as significant fluorescent quenching under solid state as well. So here is a last example, and we all know that curcumin or turmeric powder. Curcumin is one of the major ingredient or constituent present in the turmeric powder, and we wanted to actually make a theranostic agent with the help of turmeric powder, and this unit is a curcumin. We put ruthenium chlorine here in order to make a ruthenium complexes, and this is our signature molecule, that is a togar-based naphthalamide. We combined these two through metallic and coordination interaction, and this was characterized by various spectroscopic method, including single crystal X-ray structure. In the solid state, we found there was a strong pi stacking interaction that resulted in the 2+2 molecular square type of arrangement that was driven by the pi stacking interaction between the curcumin unit. And we also explored their biological activity within the HeLa cell, as well as the HCT116 and the HEBG2 cell. We can see that within the HeLa cell, the green emission that is coming from this particular organometallic conjugate, and we estimated through MTT assay the fluorescent mean the IC50 value, that means the concentration required to kill 50% of cancer cell. We compared the conjugate anti-cancer activity with the corresponding acceptor and donor, and we found that in all the three cell lines, the conjugate shows a strong killing effect. That means the low IC50 value that indicate that conjugate is more potential, even better than the well-known the chemotherapeutic cisplatin. Under the same physiological condition, almost it required 13 milligram, not milligram, micromolar concentration of cisplatin to kill 50% of cancer cell. So this is the cell viability assay curve, where we can see that the conjugate source is stronger, is better IC50 value than the donor and acceptor. But one disadvantage with this particular system is that wherever we see the sulfur containing amino acid, because sulfur has a strong affinity to ruthenium, that break the complexes. Okay, so in order to overcome that, very recently, this is unpublished work, we prepared a molecular spherical molecular sphere, which is hollow in nature. This hollow structure was obtained by reacting with the dipyridyl donor with a 90-degree acceptor, and after 3 minutes of sonication, and we could able to transform this hollow microsphere. So the red spot are corresponding to the microsphere, and the blue one is actually a nucleus strain, and we found that it is not toxic, this molecular square. So because of that, we are currently investigating whether we can use this as a stimuli responsive targeted delivery vehicle for different anti-cancer agent. And here the external stimuli which we are using, non-invasive ultrasound, because ultrasound can transform this cage-like structure. Okay, so this is unpublished work, we are in the process to complete it. So with this, I'll stop by thanking my research team at IIT Palakkad, also IIT Palakkad and SCRB for the financial support, and IRIS Research Council for the financial support and research facility. So thank you all, and if there are any questions, and I'm happy to answer. Thank you.
Thank you, sir. So for your valuable and informative lecture. So participants, if you have any questions, so kindly post in the chat box, or you can unmute yourself and you can ask your queries or doubts to the resource person. So one question from student participant.
Yes.
May I ask, yeah, sir, what type of bonding exists in supramolecules?
Yeah, so that's what I mentioned. There are many type of interaction, like many non-covalent interaction. So we are particularly interested in using coordination bond as a driving force. So basically, there is a metallic and coordination bond because of their moderate bond enthalpy and the high directionality. So there are some cases where people also have used pi-pi stacking interaction as well as hydrogen bonding interaction. So we can choose any type of non-covalent interaction. So that is up to our choice. But our group, we are interested in using coordination bond as a driving force.
Thank you, sir. So any other questions from other participants? So another question from student participant. So
Yeah.
So how do you know which non-covalent interaction is strongest?
So you know the chemical bond energy. We can calculate easily. There's several formula by which we can calculate the bond energy. So if you, that's why I told you that I'm getting an echo. I think Rajkumar, you can put it in mute.
Yeah, yes, sir.
Yeah. So if you know the bond energy by using the simple formula, we can easily calculate the bond energy. But the preferred bond energy for reversible supramolecular interaction is 50 kilocalories per mole. Okay, so if it is more than 50 kilocalories per mole, then the problem is we may get unwanted side product and we may not get the expected product. At the same time, if it is very weak interaction, we may not isolate the expected final product because that will disassemble and go back to the starting material. Okay, so we can choose the chemical interaction according to our wish, and so as I said, we are interested in coordination bond because particularly the platinum nitrogen and palladium nitrogen, they have the chemical interaction, the bond energies 15 to 50 kilocalories per mole.
Thank you, sir. So another one doubt, not from your presentation, it's a general doubt. So now for student participant, Naveen Raja. Sir, now IIT Palakkad has called for the summer internship program. Okay. Can we apply for it, or what is your suggestion?
Yes, so we are almost in the Department of Chemistry, we are planning to take almost 7 to 8 summer interns. So you are free to apply for it. Now that there is a advertisement has come, and in fact I am going to take 2 students, and my research area also mentioned and my name also there. In case if you are interested to work with me, you can when you submit your application in online portal, you select my name as well as my research area, so then your application will come to me, then I can see the possibilities.
Thank you, sir.
Hello, sir.
Yeah, Prabhu Kumar. Yes.
How are you, sir? Good to see you here.
Yeah. I'm very happy to see you, and congratulations for your paper. And so Prabhu Kumar was my summer intern 2 years before, and from his summer internship we published a paper. So I
thank you so much. Yes, sir. Actually, my question is very simple, sir. You show that one, the TAP and TB NAP. No, sir. It's a polymerized one, tri-polymerized one in your slides, sir. So we want to make a cage. How we will control the polymerization through cage, sir? We want to form cage.
Yeah. Which one? The this
previous.
Okay. This one?
Yes, sir. This one, sir. So this is
so here we obtained the polymer because we intended to make this particular polymer. But if you wanted to make a discrete assembly, you can still get the discrete macrocycle, but you have to do it under very dilute condition. If you perform the same reaction under very dilute condition, you will get both polymer as well as a macrocycle. Since the polymer is going to be insoluble, we can easily filter it out, and then macrocycle is soluble, you can isolate that. But we were not interested to make a macrocycle. We wanted to make a polymer and then use it for different application. Yeah, that is possible.
Dilution is the only method to form a cage zone, sir, or is there any method is available?
So, in this particular case, why see the one way to avoid the polymer formation is that how the reaction is happening. When you have 2 reactants, they collide each other constantly. They will collide each other. When they there are only certain collisions that reach the threshold energy, and that will result in the crossing the energy barrier. Okay. So when you increase the concentration, what will happen? The number of possible collisions going to be more. Okay, so that always leads to the product of the polymer formation. So you basically need to reduce the number of possible collisions by diluting the sample solution.
Yes, sir.
So that will reduce the number of possible collisions. Thereby, we can always try to get the major quantity of the discrete assembly rather than the polymeric structure.
Polymer formations. Okay.
Yeah.
Yes, thank you, sir. Thank you, sir.
That's not the only way, but you also need to define proper bite angle between the building blocks. So you cannot randomly select the building block and expect something. So if you are interested to make a molecular square, you need to have a 90-degree acceptor and 180-degree donor. Then only you will get a
Then we will
molecular.
form a case, a nice case.
Yeah.
Yes. Okay, sir. Thank you, sir. Thank you.
Thank you, Prabhu Kumar, for your doubt. So I forgot to share one information. We'll read out the biodata of our resource person.
Yeah.
So Prabhu Kumar is an internship student who is doing a PhD in IIT Chennai, and another internship student is also doing PhD in IIT Tripadi, I think. So I encourage the students.
Mayuri, yeah.
Mayuri, yes.
Yeah,
So
yeah. So I had 3 summer interns 2 years before. One, she was not interested in research, so she is doing something else, and the other 2 are Prabhu Kumar and Mayuri. Both are doing now PhD in IITs, and Prabhu got a paper, and the other student paper we are in the process of submitting it. So almost all my internship students will have.
Yes, so that's what I am trying to say.
Yeah.
So through this program, I encourage our students to do internship program under your able guidance.
Yeah, you are most welcome.
Thank you, sir. So any other questions from other participants? So if there is no question, let me conclude today's first technical session handled by Dr. Sanmuraju Sankrasegaran sir from IIT Palakkad, Kerala. So on the behalf of organized committee, I express sincere thanks to today's resource person for accepting our invitation to deliver a lecture on supramolecular chemistry from molecules to materials.
Yeah.
Thank you so much, sir. We are very fortunate to have you as a resource person.
Thank you very much. Thanks to Kanapati Anna as well. Kanapati Anna was my inspiration during my undergraduate study. He was doing master degree. So thanks to him. I'm meeting him after a long time. Yeah. Thank you very much.
Thank you, Sanmuraju sir. Thank you. It's nice to see you here, keeping things very simple. Thank you so much.
Yeah.
So,
Sure.
I expect you to be in our campus as soon as possible when you visit at Madurai.
Sure, definitely. I come every weekend I come to Madurai. So
really?
no yeah.
Okay, then it's fine. Anyway, I talked to you over phone. Thank you so much.
Sure. Yeah, sure. Thank you. See you then. Bye.
Yeah, bye.
So the first technical session has come to an end, and I hand over the session to Dr. Elayradha, Assistant Professor of Chemistry, Vivekananda College. Over to you, sir.
Yeah, thank you, Raj. May I audible to you?
Yes, L.I.
Yeah, thank you so much, sir. Undoubtedly, for the past 1 hour is most informative and created an enthu among the participants, we believe. And we are the host today and you are the guest. And today you justify this word by showing an expo gate on supramolecular chemistry in terms of your research observation. Hope all the participants are benefited in all aspects via your informative delivery. On behalf of the organizing team, once again, I personally thank you, sir, for your wonderful lecture. So in this regard, I also extend my sincere thanks to my friend, Dr. G. Rajkumar, for your wonderful sharing. Thank you so much.
Thank you.
Yeah, Ganabhai sir, shall I start this session? Or
Yes, yeah. There is no break. Then another resource person, Arindam Indra, sir, is already joined with us.
Okay,
sir, good morning, sir. Arindam Indra, sir. Or can you hear me?
I can hear you. Can you hear me?
Yes, exactly.
Okay, good morning. Good morning. I am presenting from desktop. Okay, so you cannot see my photo.
Okay, fine. Anyway, thank you for joining very in advance. And first of all, as a convener of this program, let me thank you for keeping things very simple because you didn't show anything complication. And thank you so much. We are really proud to have you, sir. Anyway,
thank you.
Now, Elayradha, you can start the procedure. Yeah.
So nice from here. And now we are moving to the technical session 2. As I already said, today we have 2 big shots and one lecture is completed in a wonderful manner. And now we have the great Professor Arindam Indra from Department of Chemistry, IIT Varanasi, Uttar Pradesh. And I am very happy to brief about his bio sketch. Sir has completed his BSc at Hooghly Mohsin College, the University of Burdwan, West Bengal. And Sir has also completed his MSc Chemistry from the same university during 2006. Sir had completed his PhD program in the group of Professor the great G.K. Lahiri from IIT Bombay, Mumbai. Coming to his professional experiences, to till date, from 2018 onwards, Sir has been working as assistant professor at IIT Varanasi. He also worked as assistant research professor at Haenyang University, South Korea during 2016 to 2018. He also acted as a group leader for the catalysis and synthesis group Basquiat, Berlin, Germany during 2015 to 2016. Sar has also acted as a postdoctoral research associate in the group of Professor the Great Matthias Dies at Dessing, University of Berlin, Germany. His area of interest is artificial photosynthesis, energy conversion, metal organic framework, derived catalyst for energy conversion, photocatalytic organic reaction with quantum dots and semiconductors, bio-inspired electrochemical oxygen evaluation reaction. Sir has completed three major projects from various funding resources from like CSIR, DST, SERB, IIT, Varanasi. Net worth is around 52 lakhs. And his, coming to his citation, his H index is around 38 and total citations around 3,810 and I index is around 41. And after looking his publication, I really astonished because Sir research career has crowned with plenty of beautiful publications like Chemcom, AngioND, Energy of Environment Science, and even JAX also. So with this short bio sketch on behalf of the organizing team as well as the convener, I'm very happy to welcome you, sir, to our campus through this e-meet. We are expecting your wonderful lecture, sir. Please.
Yeah, thank you very much for the introduction. Okay, so I want to thank the organizing committee for inviting me this lecture. But I will be really happy to be there personally one day. But yeah, this situation is not allowing us to like deliver a lecture personally. But personally, I like it to deliver a lecture in front of all the students and all the spectators. Anyways, let's start. First, I'll try to share my presentation. But please be response sometimes that sometimes I have seen that in this Google Meet there is a problem that your slides is not moving. If I am moving also, if you see some discrepancy, please inform me.
Yeah, sure, sir.
So just put on your mic, switch on your mic, and then just stop me. Okay, so I will keep it very simple, the presentation, and as most of the here students, so I will try to keep it as simple as possible. Even class 7, 8, if you have the knowledge of class 7, 8, you can understand most of the things. I will say that 90% of this thing you can. So I hope that you have seen the title of my presentation. Like I have given it, I can give it different title also, but as it was given that it's from green chemistry perspective, so I have arranged the title like that. Integration of organic reactions with electrochemical water splitting, a perspective from
Sorry
green
for
chemistry.
the introduction, sir. Make it a slideshow, sir.
It's not visible?
Yeah, your screen is there, but it's not slideshow, I hope. Just
But
make it as a slideshow, sir, and just move one slide, we can confirm.
Can you see it? I'm in the second slide.
No,
sir.
not really, not really.
No, sir, not moving, sir.
The same thing has been happened for the previous speaker also. So what he has done is, he just changed into PDF file, then it was fine. That's the best thing.
Okay, so then it will take some time if I have to change it to PDF file.
Just save it, sir. So just give him save us and you can do it. I think so.
Okay, so then give me a few minutes.
Yeah, that would be nice.
Okay, fine. Save as. Okay, so I will feel a little bit of problem because I have some animation, but anyways, no problem. Leave it. Let's say that how it is looking like in PPT. It's fine now?
Yes, sir. You just make it full views.
Oh, okay, fine. So one thing I think you people will miss that there are some animation. So I am going to you are going to miss that one. But anyways, that will not affect that much. So okay, so I have to make it full view.
Yes, sir.
Can you help me how you can go?
Sir, can you do it as a full screen actually?
Is it now possible? You can see full view or not? This is full view for me. Is it okay?
Not yet for me. Let me check.
Yeah, even for me, it's just hanged.
And okay. This thing. Yes, now it is.
So now it is fine, sir.
Okay, fine. Let's start. Okay. So what I was talking about that as this session is about the green chemistry. So I changed my title accordingly. So the title of this presentation is Integration of Organic Reactions with Electrochemical Water Splitting, a perspective from green chemistry. So as you know that we are working in this field for the last, I can say that my experience that I am working in this field for the last, at least last 20 years. So the same field is chemistry, green chemistry mostly, and mostly catalysis. So catalysis is a part of green chemistry. Let's see that how we can utilize this catalysis for green chemistry. So we'll start from green chemistry. What does it mean? Then we'll come to energy conversion. And then third part, we'll discuss about the organic reactions in especially electrochemical organic reactions and how we can integrate those with electrochemical water splitting. So that means energy conversion and organic reactions simultaneously we are trying to like utilize in our labs. So here, first we'll try to understand that what does it mean, green chemistry. It's very preliminary. Again, I am saying that any BSc students can understand this. So definition wise, I'm not going to again define what does it mean, but exactly green chemistry means we have to minimize the hazard for a chemical reaction. And for that, we need to develop a process. It's not only the minimizing the chemicals, whatever available, or use of less amount of hazardous materials. It's not like that. It's the overall thinking. You can say that it's a philosophy, how we can develop a method, how we can design some sustainable process so that we can produce less hazard, we can use less hazard, and we can make a sustainable process. This is the main thing. So that means we can produce less hazard by some reactions, but you can understand that when you are doing a reaction with a very toxic chemicals, then the problem will come here that ultimately you are exposing your body or your whatever you're taking breathe anywhere internally and externally, you are exposing with a toxicity. So that means use of toxic chemicals also you have to eliminate it. Totally elimination is sometimes not possible, but what we have to do as much as we can minimize these hazardous chemicals. So that we need a process. What does it mean, this process development? Process development means that we can design new catalyst, we can design new reactor, we can treat the products, that means side products, we can minimize the production of side products, and at the same time we can utilize very simple thing that avoid as much as possible toxic chemicals. So basically this green chemistry will give you like a disciplined life. Mostly what we can say that at this moment we are not able to go back to our old days, like say 100 years ago, that where there was use of chemicals was very less. No, we cannot do that. It's not possible. So what we can do that we can minimize the hazard. So this product and process is very important to design catalyst. And if we look at that, what does it mean, a catalyst? Especially, I'm not going to define that what is exactly catalyst is doing, but you can see that from a green chemistry of perspective that we can simultaneously use one word, atom economy. What does it mean? Atom economy or atom efficiency, we can define that how much like unexpected product, that means side products we are preparing by a chemical reaction. So this unexpected products means that our side product means that how you can prepare all these things, unexpected product, you can minimize this thing. That means we need a catalyst. Very simple thing. Now let's say, what does it mean, atom efficiency? So atom efficiency is, the definition is molecular weight of desired product. That means the product you are going to prepare divided by molecular weight of all substances formed. So basically it is talking about the number of side products you are doing. So if we look at that, one very simple reaction, which is 1-phenyl ethanol, this is like a classic class, like I used to take BSc classes, MSc classes, I used to give the same example. So I have taken the same example, this is 1-phenyl ethanol. We want to make a simple one-step oxidation, so we want to make it acetophenol. So if we want to do this reaction by stoichiometric oxidation, what will happen? We need chromium oxide and then H2SO4. Alkali medium, this reaction will not happen. We need an acidic medium. So this acidic medium, the reaction will proceed and you will get 1-phenyl ethanol to acetophenol. But with that, we are going to get a huge amount of chromium sulfate and this water also. Now you can ask me that how water can be toxic. Yeah, very simple thing, that water is not toxic. But here we have to consider that this water, whatever we are producing, that is mixed with chromium sulfate. And if you want to purify this water by different techniques, it's a huge task. Basically, your water, whatever is produced in this reaction, is equally contaminated and equally toxic. So if we look at that, this atomic efficiency of this reaction, this uncatalyzed reaction, according to this formula, you are getting only 42%. So that means only 42% of your atom is utilized and rest 58% not utilized for your desired product. So it's a very low value. It's not expected. It is unexpected. But let's see if we do the same reaction in presence of a palladium catalyst. PDPPST whole 2, you can take it, but better to take a water soluble catalyst here. So you can do the same reaction, and what will happen, that your atomic efficiency of this reaction will be improved to 87%. So this is the role of a catalyst. Catalyst basically increasing the atomic efficiency of a reaction. And that's why nowadays in all over the world, industry, mostly industrial process, more than 90% is catalyzed reaction. So catalyst not only improving the atomic efficiency, this is just one aspect from the green chemistry perspective. It is basically what is doing. It is doing many things that will come to this point, but let's see that what is the present scenario. If I say it's very important, but how you can know that is really, we need some proof. So if we look at that, the last year, 2021, the Nobel Prize was given to Professor Benjamin List and Professor David Macmillan for the development of asymmetric organocatalysis. So what does it mean? Organocatalysis, they first have shown that organic molecule can be catalyzed. And at the same time, asymmetric means asymmetric synthesis, organic synthesis, that means chiral molecule synthesis. So this is 2021. Now, if we look at the scenario for the last 20 years, in 2010, it was given for the coupling reaction to Professor Heck, Professor Negesi, and Professor Suzuki. So we all know all these things, that Heck coupling, Negesi coupling, and Suzuki coupling. Next, in 2007, Gerhard Ertl, he got it for the solid surface chemical reaction, basically catalysis process, how it is happening on the heterogeneous catalyst surface. In 2005, it was given for the metathesis reaction to Sauhin, Grafs, and Stock. And if we look at that, 2001, it is given to Knowles and Naoki for the hydrogenation reaction, and then Very Surplus for the oxidation reaction. So on, we can see that this is such an important field that last 20 years, at least few years it was given to chemistry Nobel Prize only for this catalysis. And if we look beyond 2000, it was again, it will add few more. At least you know that Ziegler-Natta catalyst. So looking at this point, let's see what does it mean, how it is happening, catalysis, although you know it, but I am repeating it again. That catalysis mean, if we want to do a thermodynamically favorable reaction, that means substrate A is here and here it is product formation B, it is thermodynamically favorable. Then what is happening that if you have to like roll on this stone from here to here, that means you have to like cross this much of distance, this much of height, basically. But if you make a tunnel in between, then you can go through very easily. So basically catalyst actually making a tunnel. Scientifically termed that what is catalysis doing? It is reducing the energy of the activation. So here you have a transition state, and this transition state, actually the energy is getting reduced by, we can reduce it by using a catalyst. And we can easily go from A to B, that means substrate to product. So this is talking about the speed of a reaction. That means kinetics of a reaction. So using a catalyst, we are speeding up a reaction, we are increasing the rate of a reaction. Now this catalytic reaction, we can do it in different way. First one, like very common one, whatever we are doing in the reaction, let's say we are doing a reaction in room temperature, but still it's a temperature, room temperature. So that means we are talking about a thermal reaction. We can do it a photocatalytic way, that we'll call photocatalytic reaction, and we can use this last one, electro, and many others when I am not mentioning here. We can just like rub it with a mortar and pestle, we can try to ground it. So that is a mechanical force we are producing. That can be also a catalyst.
Sir, sorry for interruption. I'll ask you one simple, very basic question, sir, here.
Yeah.
Yeah, because actually, very recently I come across the word, we cannot use the catalyst for the reaction which reduce the rate of reactions. So that we have to use only inhibitor. Is it true or right, sir? Because before that, what I was know is, because we have to use the catalyst is nothing but it's just alter the rate of reactions. But recently I come across the term, so we should not use the term catalyst if the catalyst reduce the rate of reactions. Is it true or what's your opinion on this, sir?
See here, I can say I am actually agreeing with the term, actually inhibitor. It should be inhibitor. We can say that catalytic inhibitor. Now this is very simple way, we cannot say it is catalytic reaction or it's a inhibiting reaction by inhibitor. It's not possible to say, we just looking at the rate of a reaction. Okay, we have to look at the mechanism. Apparently, let's say one reaction is going on without catalysis, without using any catalyst. Okay, but rate is getting reduced. Okay, so that's what I was not going to discuss, but anyway, this is a very good question. So what is happening, that catalyst we are not going to use always for the rate, increasing the rate of the reaction, though that's the very primary concept for the BSc students or MSc students. But many times we are using a catalyst to increase the selectivity of a reaction. And if we want to increase the selectivity of a reaction, many times we have to reduce the rate of the reaction. A fast reaction can give you multiple products. Okay, so that reaction we cannot say it's the inhibitor. That is, we cannot use the term inhibitor. So that means the mechanism of the reaction is very important. If we see that rate is getting reduced, we cannot come to a conclusion that it's an inhibitor. No, it's not true. We have to look at the rate of the reaction, and definitely that's a primary criteria. But if it is increasing the selectivity of the reaction, we'll use the term catalysis.
Okay, sir. Thank you for a nice explanation. Thank you, sir.
Okay, fine. So that means catalyst can do multiple things. It can increase the rate of the reaction. It can reduce the cost of a reaction. It can reduce the temperature, pressure, all those things. But at the same time, most importantly, a catalyst can improve the selectivity of a reaction. So that part I have not used here because today I am not going to talk about normal organic reaction, thermal organic reaction. Especially I am talking about electrocatalytic reaction. So their selectivity automatically we are getting. There was no way to control. Better to say that there is no way to control. So let's see that what does it mean electrocatalytic reaction. So this is the third option what we are talking about. So electrocatalytic reaction, again, it's a flow of electron. Basically, any type of reaction we are talking about is a flow of reaction. But here, what we are doing in this electrocatalytic reaction, you can say that in an electrochemical setup, the electron acceptor and donor both are same. That means electrode. Not same, I will say that two different electrodes. One is cathode, another is anode. So in cathode, there is a reduction is happening. In anode, oxidation is happening. And here, one more important thing that it's most of the electrocatalytic reaction we can carry out at room temperature. So we are avoiding high temperature, high pressure, all these things. Even we can do that, but at least at this moment, what I am going to discuss here, I want to keep it simple. That's why I am saying that we are not using high temperature or pressure for this type of electrocatalytic reaction. So cathodic reduction, it can be energy conversion as well as organic reaction. So energy conversion, we can say that hydrogen evolution, oxygen reduction, nitrogen reduction, CO2 reduction, nitrite reduction, and organic reactions. Whereas anodic oxidation reactions, it can be oxygen evolution, hydrogen oxidation, all these things, it's written biomass oxidation. But most of the important thing for this electrocatalytic reaction nowadays, previously, you know that all this thing about Arrhenius theory, all this thing. But what is now people are using electrochemical things, electrochemical setup, mostly for the energy conversion, and that also sustainable energy conversion. So which is the main part of the green chemistry, that's sustainability, and at the same time, green synthesis of the valuable products. So here I am missing the animation, but anyways, that's not going to give any problem. So what is happening here that when we are talking about electrocatalytic energy conversion, so first I want to say that what is the importance of electrocatalytic organic reaction, energy conversion. So first thing we have to think about the demand, that why we need electrochemical conversion. So if we look at the current scenario, everybody were aware of that global warming, climate change, and then air pollution. So these things worldwide, everywhere it is discussed. Initially it was neglected by all over the world. It's a political agenda. All world leaders, they are neglecting because it was not affecting their countries, mostly Western countries. And we can see that last year, 2021, in July, the temperature of Paris was 43 degrees Celsius. So it's a really, really warning situation. Whenever they neglected it, it's now they are also equally suffering. And we can see that this tornado, which was a very common phenomenon in the US, now it's coming to India also. And we can see that the southern part of India, and especially the eastern part, like Bengal and this Bangladesh, this part is highly affected. Again and again, the tornado is hitting these parts. So we cannot avoid this thing. It's a worldwide phenomenon, and we have to think about that how we can eliminate, or at least we can reduce all these problems. So mostly we have to reduce the temperature, or at least we have to keep it constant, the situation. And for this part, 2019, there was a Paris Convention. So there it was just proposed that the world temperature till 2050, it will be exactly like only 1.5 degrees Celsius increase. If it is more than 1.5 degrees Celsius, like 1/3 of the land will be underwater. And you can see that this is a very iconic figure is the Maldives president. So he's doing a press conference underwater, and they are really there like requesting all over the world that please reduce the use of consumption of fossil fuels. So this fossil fuels is the main culprit here, that if we use this fossil fuels, this is producing greenhouse gases, and that is causing the global warming and then climate change and all these things. So anyways, so this thing that we have to think about, that how we can reduce the consumption of fossil fuels, that means petrol, diesel, all these things, and we have that alternative on energy. So basically, we need alternative energy like sustainable energy. So we can talk about this wind power, we can talk about hydroelectricity, we can talk about solar power. And this solar power, you know that it's like we have enough, more than enough solar cell. But the problem is that the solar cell, we need a huge expensive system, and then all over the world we cannot use it because everywhere they are not getting equal sunlight. And the problem is that we cannot store it is very efficient way. That's the most problematic things nowadays. So what we can do, we have to think about that energy which we can store. The storage of energy is not only energy conversion. At the same time, storage of energy is very important. So storage means we have to prepare fuel. That fuel can be taken to anywhere. It could be like Mount Everest, or it could be Mariana Trench. Anywhere we can carry out. But in the solar cell, we cannot carry out there. So that's why we need fuel, like petroleum, like diesel, like that. So for that, one of the important thing is that we have to think about alternative fuels. Basically, it's the better term to use that alternative, not only alternative energy, but we have to think about alternative fuels. But if we look at the recent scenario of the sustainable energy, world is now using around 13 to 15% of alternative energy. And few of the countries, they are really like progress so much that they have using more than 100%. There is a reason the what I am saying that it's unscientific, but still they are using the more than 100%. That means that they are producing excess of sustainable energy. Like a country like Denmark, they are producing 140% of energy. That means whatever they require, extra 40% energy they are producing by sustainable way. So some of the part like Scotland, they are also there, and we have also the airport in Kerala that where you can see that it's totally solar powered. So it's possible. But let's say more than 13%, only 13%. So we have to think about that more than 13%. So that's why we need sustainable fuel, green fuel, and that could be hydrogen. That is the main important thing. Still now we can talk about hydrogen. And if we think about hydrogen production, this main thing that it has a very high calorific value. This high calorific value means if we burn it, it can give the energy which is at least 100 times better than petroleum. If we burn the exactly same amount. So if we look at that, this hydrogen production, this nature, there is few bacteria, all these things they are preparing, they are producing hydrogenous activity that we can say, but that's a very less amount, and the basic molecule like hydrogenous, so that is catalyzing the reaction. But if we look at that, if we try to look at the nature, where the main energy conversion is happening, that is called photosystem. So that's because we're talking about the photosynthesis that's happening in like the green plants. So this photosystem, you can see the structure here, that this is a very complicated structure, mostly surrounded the protein molecules, all these things. But the basic thing which is more important from the inorganic chemistry and biology, that's this cluster. And this cluster is consisting Mn4CaO5. That means 4 manganese, which is color is purple here. I don't know how much you can see the color difference. The red one, that is oxygen, and calcium one is the green one. So this is the cluster. You can see that is a mostly like a cube structure. One hanging manganese center is there, and WW means 2 water molecules are there. So these water molecules are basically working as a substrate for the water oxidation. So this water oxidation, what does it mean? So here again, there is a problem in conceptually we faced in our class 11, 12 books or class 10 books, that photosynthesis, the definition is given wrong. That it's written that photosystem means production of glucose from carbon dioxide. So this is totally wrong. This was last like say 10 years I am trying to give the impression that's totally wrong. No, photosystem or photosynthesis is not the carbon dioxide reduction. That's a dark reaction. That's not a photoreaction. What is happening basically in photoreaction, that water is getting oxidized to oxygen and it is producing 4 protons and 4 electrons. So these 4 protons and 4 electrons, these are basically our energy source. We can say that. These electrons reducing carbon dioxide, these protons actually helping that process. So this is a proton coupled electron transfer reaction, and carbon dioxide getting reduced to carbohydrate, and that part is happening totally in dark. No sunlight, no light is required for this reaction. So photoreaction, that means the energy conversion, is the most important reaction. We are producing electron. Simple thing, that whatever we are doing in a solar cell, from sunlight, from the photon, we are producing electron. Same thing in nature also. There is an antenna that we call chlorophyll, which is absorbing the light, and this P680 and transferring the light to this cuban, that is Mn4CO5 cluster, and this cluster ultimately converting water and then ultimately electrons and protons. So this is the reaction energy conversion procedure. So now how we can utilize this process, how we can integrate this thing with normally our electrochemical system. So we can take solar cell, we can charge a battery, and ultimately we can electrochemically produce hydrogen. So no need to charge a battery from other sources. And ultimately this hydrogen, this fuel, here H and H, hydrogen bond, that bond actually like storing the energy of this whole process. So basically storing the electrons. So this process, we can convert that solar energy to hydrogen, that means chemical fuel. So it's the interconversion of chemical energy to fuel energy, chemical energy to electrical energy, or electrical energy to chemical energy. This way we can think about. So the whole procedure, that means first thing, it will start from a solar cell that will charge battery. That battery will be used for the electrochemical hydrogen production, and that will produce hydrogen. That hydrogen is a chemical fuel, and we can use it anywhere in the world. And we know that it is it's not something like we're talking about utopia. No, it's like now country like Germany, they are running the trains hydrogen with hydrogen, and that's little bit expensive. And I'm really happy to say that I was involved in that project. So it's a huge task for us that we are working continuously 5 years from around 20 labs around all over the Europe. So to produce hydrogen and utilize it. So it's physics, material science, engineering department, equally they are working together to make it feasible. So we have seen it that, yeah, our project was running successful. A train can be run with hydrogen fuel. So it's a very practical thing. It's not something utopian. So let's see how it's happening. So the thing is that water is producing hydrogen and oxygen. This is a very simple reaction looking like that. And at the cathode, we are getting hydrogen, and anode, we are getting oxygen. So apparently it's looking very simple reaction. But what are the problems associated with here? That this oxygen evolution, this is actually 4 electron, 4 protons, they are associated with this reaction, and it's a multi-step reactions. At least 4 steps are happening here, all have very high activation energy. So this is basically reducing the overall process efficiency of the overall process. So we need to develop the oxygen evolution reaction or anodic reaction. Hydrogen evolution reaction is not a concern. It can be automatically developed if we can improve the anodic reaction, because these are the 2 coupled reactions. We cannot separate these 2 reactions, because oxidation and reduction, when we are talking about a circuit, so we have to complete the circuit. That means we need cathode and anode equally active, equally efficient. So from this part of point, we are working that how we can develop anodic catalyst, which is highly efficient. That means it can do this oxidation of water to oxygen very efficiently. So let's see that what are the scenario recent, that whatever we are talking about, that is the 4 electron proton transfer reaction, and at the same time it's thermodynamically also high energy is required, 230 kilojoule per mole. And commercially available iridium oxide, ruthenium oxide, they can do this water oxidation reaction pretty efficiently. But the main problem that we cannot use iridium oxide, ruthenium oxide for commercial purpose, because it's the highly expensive one. Even more expensive, iridium is more or less more expensive than platinum even. So it's not possible, it's not a feasible or practical solution. So what we need some material which is low cost, eco-friendly, and naturally abundant. So this thing could be transition metal catalyst. So this transition metal catalyst, I don't know, it's looking very bad here. So, but I can read it that it's mostly 3D transition metal: titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. Then we have iridium, niobium, ruthenium, all these things. So those things I am not going to mention here, but at least we can talk about that if we want to design high oxygen evolution catalyst, mostly we have to think about nowadays. It's very simple. It's well known that cobalt, nickel, and iron, Fe. This cobalt, nickel, and Fe, these three metals mostly producing the efficient catalyst. What are the reason that I am not going to discuss today, but you can try to read it, that why these three metals, not other, why these three elements. And we can use its oxide, hydroxide, phosphide, chalcogenide, all these different things. And for hydrogen evolution, we can use alloy, phosphide, chalcogenide, carbide, all these things. No need of using platinum. Let's see that how it is happening, parameters of water splitting and how it is working here. So in electrochemical synthesis, we used to get like a graph like this. So right hand side, I think you can see my cursor here. So right hand side, the red one, it is talking about oxygen evolution. We'll get a graph like this. And here the thermodynamic potential, 238 kilojoule, that will be converted to 1.23 volt or electron volt. So this is the potential for the thermodynamic water oxidation potential. So what we have to do, this graph should come as close as to possible to 1.23 volt. And hydrogen evolution, it happens with a 0 volt. So that means this should come this side, left hand side, and here a particular potential that is called over potential. That means extra potential required to proceed this water oxidation reaction more than 1.23 volts. So that means whatever potential you are getting, you have to minus it. That means subtract it 1.23 volt. Okay. So let's see that next slide, it will be more clear. So if we look at this right hand side, this one, so this is a linear sweep voltammetry, very close to a cyclic voltammetric technique. So what is happening, that you can see that here the green one, but here we have to just pull out this one to the left hand side. So as much you can take it to the left hand side, your graph, this one, that means your catalyst is better. So this is reducing the over potential. So potential means extra potential required to water oxidation than the theoretical potential. Now with that, some other things are happening. We have to consider another thing is that a catalyst is very active. That's the primary phenomena. But it should be very stable one also. Let's say your catalyst is very active for the 10 minutes. It's not going to work. At least it should be stable for at least for a few months. So for that, what we have to do, that we have to think about the stability of the catalyst. That could be measured in chronoamperometry or chronopotentiometry. So this is a constant potential or constant current density. These two ways we can measure it. Different two techniques. So, okay, so I'm not going to detail of the techniques. I'm not talking about, but at least we should know about that these two techniques, chronoamperometry or chronopotentiometry, we can carry out to understand the stability of the system. And if it's a stable system, it should give a straight line with the time, and it should not like decrease with time. So that means current density or potential should not decrease with the time. And one more important thing, that kinetics of the reaction, that could be measured from the Tafel slope at a semi-stationary condition. So semi-stationary condition means that the change of this reaction condition is very slow, very slow. So this Tafel slope basically talking about the kinetics of a reaction, how fast a reaction is or how slow a reaction is, and their low value is better. Okay. So now what is happening, that if we look at a cyclic voltammetry, so it looks like this. It starts from, let's say, particular value, let's say 0, and ultimately there is a hump here, and it looks like this. And again coming back, and again a hump here, and again like that. So we can divide this cyclic voltammetry in 3 different parts. The first part, you can see that there is a blue colored thing. So this is a non-Faradaic region. That means there is no electrochemical things. That means no redox process is taking place here. So basically here electrochemical double layer is producing here, and this from this electrochemical double layer we can capacitance measurement we can determine the electrochemical surface area. That is one of the important factor for the water splitting. Second, this Faraday region, this purple color, where you can see that a hump. So this hump is basically talking about the change of the oxidation state of your material. And at the same time, we can determine from this change of the oxidation state number of active sites, which is one of the important factor again for the water splitting. And this red region, overhead potential, so that I have already discussed, it is talking about the activity of the catalyst. So here you can understand that I am detailing all these things. There is a reason that just a CV, that means a cyclic voltammetry, is enough to understand so many things of a catalyst and its catalytic process. We don't need multiple techniques. We don't need multiple spectroscopy. Nothing is required. Here, at least you can get a preliminary consideration and preliminary information from a CV that how active your catalyst is, what is happening in Faraday region, means how the oxidation state of the material is changing, and at the same time you can get something electrochemical surface area and number of active sites. So one CV is enough. Now the fourth point, that which is also affecting the water splitting, that is charge transport. That means your electrons or protons how easily moving inside the solution, and that we can measure it from the electrochemical impedance spectroscopy, and their lower radius, it is actually showing that it is mostly conducting. That means lower resistance. So lower radius means lower resistance. Okay, so we'll move to the other factors, which is highly important factors. I will say that those are mostly electronic factors. So if you want to design one water oxidation catalyst which is highly active, first we have to consider that should have some mixed valency. That means let's say we have cobalt. Cobalt should be in +2 oxidation state, +3 oxidation state, and eventually it will be converted to mixture of +3 and +4 during water oxidation. It should have some coordinatively unsaturation. That means cationic vacancy. It's where the substance can bind easily. That means water can bind easily. So it's a very simple phenomenon for any catalytic reaction that there should be a binding site. Some cationic vacancy should be there that will improve the coordination and saturation, and then tunable interlayer distance. So this is atomic level thickness talking about. So I will discuss it again in the next slides. But these 4 and then previously 4, so total 8 criteria we can actually finalize which are affecting the water splitting. Now the question is that, is it really possible to design a design a material which can fulfill all the criteria mentioned here? And that's the question, that's the big question. And for that, all over the world people are working that how we can combine all these factors in a single catalyst. And for that we have come to a different thing, that we have come to our own solution. I'll discuss it, but let's say that what is the most prominent one if it is fulfilling all these things. So that is called layered double hydroxide, this catalyst. So in abbreviation we'll use the term LDH. Okay, it's a very common one, layered double hydroxide, LDH. So what does it mean? You can see that this left hand side blue one, it's a layer of hydroxide. Let's say it's the cobalt hydroxide. Again another layer, and in between you can see that some different molecules are there. But you can see that right hand side there is a formula is written, it's cobalt hydroxide. Don't think that cobalt is in +2 oxidation state only. No. In layered double hydroxide, some of the cobalt atoms they are oxidized to +3 oxidation state also. So basically you are creating a imbalance in the molecule that it's +2 and +3. So only OH2, it cannot balance or compensate the charges. So what is required? In between the green things, it is basically talking about anion. And with this anion, another layer of cobalt hydroxide is interacting and so on. So we are making a layer by layer structure, though the interaction between two layers is very weak one, but it's basically different types of van der Waals and ionic forces. So with this, we can see that why this material is important, because this is a layer structure. So water or electrolyte, it can go inside these layers and it can come very close to this your catalytic site, active sites. This is first thing. Second thing, that it has a very high electrochemical surface area. Third thing, that electrocatalytic sites are accessible and we can change that this is gap between two different layers by changing the molecule in between. So it could be carbonate, it could be hydroxide, even it could be like say benzoic acid or terephthalic acid. So that means we can tune the gap between two different layers, which is highly important for the water oxidation activity, because according to catalytic activity, catalytic mechanism, it should be tunable. And it has a 2D morphology also, that is important. So looking at all these things, that we will see that how it's working. So you can see that nickel iron cerium LDH, which one of the best water splitting activities, showing that 175 millivolt for oxygen evolution, so very low value. NiV ruthenium, that is also 12 millivolt for hydrogen evolution, like that. But what are the demerits? There are some demerits also, it's not the only solution. Demerits that it is basically kinetic wise very slow, number one. Second is that conductivity, electronic conductivity is very poor, but the most important thing, that stability is very low. So it cannot be the ultimate solution. Though it can produce very high activity for few moments or few minutes, it is not ultimately the solution. So what is happening? One approach is the self-supported approach, the red one, we can see that. That means we have to, like say, immobilize the LDH on a solid support like carbon cloth, nanofoam, like that, which are highly conducting. Or we can use some conducting material with the LDH like graphene, carbon nanotube, endope carbon, all these things. Okay, so this is the ultimately two different solutions. So what we are doing, that we'll discuss here, that we are using the first one, that's why it was a red mark is given here. But before that, we can further improve the activity LDH, make it ultra thin. That means, let's say we have this one layers by layers, so we can take out one by one layer. What will happen? That if we take one by one layer, it will further increase the surface area, and ultimately all the surface is available for the, theoretically, definitely, not always practically it's true, but theoretically all the surface from the top and down, all are available for the catalysis, and lot of coordinatively unsaturation is present there. So one single layer is the best option. And what we can do? We can do the exfoliation. So this exfoliation, one is that top-down approach. That means we can take some bulk LDH, and then we can use sonication for long time to weaken this force, that is van der Waals force between the different layers. So what will an ionic force means definitely there is some ionic force also there. So if this thing is happening, that we are reducing the van der Waals forces and then ionic forces between different layers. So what is happening, that by this exfoliation method, we are getting single layer. But during this procedure of thing, what is happening, that the sonication, it's a very high energy technique, and we are basically breaking these bonds, but at the same time, we are breaking the layers also. So we are getting fragmented nanoseeds. So this fragmented nanoseed is the problem, and most importantly, the procedure is not scalable at all. If we do it, if we start from 1 gram of layered double hydroxide, we can get the single layer maybe 20 milligram. So it's not at all a scalable techniques. So what is happening, that we have to think about a different technique. That means this cutting of different layers, we have to use a different technique. So this sonication is not a good way to use it. But you can see here that how a single layer is looking like. So you can see that it's almost transparent layers are there. This is basically a layered double hydroxide. Maybe the morphology is not so interesting for it, for like students, but the thing is that it's like this. It's Hello? Any problem?
No, sir, can you?
Hello?
Sir, can you hear me?
Yeah, I can hear you.
Yes, sir. You can proceed now.
Okay, fine. The morphology is good. It may be not so much fascinating for the students, but it is the ultimately goal. If we can prepare some layered double hydroxide, which has some nanometer of length and its thickness is few nanometer, like 1 to 2 nanometer, it could be the ultimate solution. So what we are doing here, we came out with a totally different techniques, we'll say that, and it is like starting from scratch. What is reported that metal organic framework, which is very well known catalyst, and metal organic derived materials, which is very well known for the water oxidation. So derived material means it is oxide, hydroxide, phosphide, nitride, carbide, all these things. And all the papers, they are saying that like before, whenever we started it in 2016, that everywhere it was saying that metal organic framework, it is very highly porous material, it's a very important thing and something like that, but it cannot be directly used for the water splitting because it is not stable in anodic water oxidation conditions, and it is totally getting what I'll say, that it is totally destroyed. The structure is totally destroyed. This was the information. So now let's see that what does it mean metal organic framework. So it is used for the gas absorption, it is used in the medicine and many other things. It's a very efficient material. So metal organic framework is metal is there and ligand is there. So they are holding hand together one by one, they're holding hand, and ultimately you can see that a very nice arrangement is forming with metal and ligand, and ultimately we are getting a crystalline material. And here you can see that one void space is producing. So this pore is very important, and you can control the porosity and void space and then surface area, all these things you can control it, and ultimately you can get a very important like say tunable material. And it is used even for the organic catalysis also. Metal organic framework is already mentioned. But what is happening that this material, all the reports are saying that you cannot use it for the water splitting, but you can use it for the battery. It's a very good material for the battery. So then from there we can start it, and we can say that how we can utilize this, like say, instability of this metal organic framework to a very particularly important things. So what we have to think that we have to take something which metal organic framework can undergo dissociation or destruction very quickly or very easily. So from there we have taken Prussian blue analog. Okay, so I will explain that what does it mean Prussian blue. Everybody, we are familiar, chemistry people especially, that if you want to detect like say Fe3 and we used to add that K4 FeCN6 and we used to get a very nice blue color, our BSc labs experiment, that Prussian blue. So this Prussian blue, if we replace this Fe with other metals like vanadium, chromium, manganese, cobalt, nickel, like that, what we can get, that we can get an analog structure. It's the same structure, basically, only the elements are different. It has a 3D morphology and highly porous one structure, easy charge transfer and tunable properties, and it looks like something like that. You can see that how nice structure all these molecules. So cubic, spherical, or some hollow structure, and all these things, hexagonal, all these things. So we can prepare more different morphology, nice